Today I am going to perform the experiment in which we have to determine the wavelength of sodium light. This is monochromatic light with the help of the Fresnel Bi-prism. So we're going to find out the wavelength of sodium light, and the method we are going to use the Fresnel Bi-prism. The apparatus which we have to use is optical bench with uprights and sodium vapor lamp for the light source, and then a bi-prism, slit, and micrometer eyepiece, and of course there is a convex lens. Okay, so this is, you can see, this is my optical bench. So let me, these are this is my optical bench, so, and these are my uprights, 1 to 4 uprights I am going to use. So let me first get all these from the optical bench. So this is my optical bench, and this is my sodium vapor lamp for the light source, and this is the slit, you can see, through which the light will come. And before performing the experiment, what I have to do is we have to balance this optical bench by using you can see the spirit lamp. So with the help of these screws which are there at the end of the optical bench, and so the level should be same. So use the spirit lamp, you will use the spirit lamp. So I have already balanced it, use the spirit lamp, and at the end, at both the ends and the middle and overall, to balance the optical bench. So and you can see this is my Fresnel Bi-prism. You can see this is the Fresnel Bi-prism. You can see here, this is a kind of the one side of the prism is plain, and the other side we have a slight curve. You can see this line, this is a slightly, like the base of the two prisms are attached together. You can see here. Okay, see, you can see this line. Okay, this line. So this is my Fresnel Bi-prism. We will mount it there, and then we will have to use a lens, convex lens. This is my convex lens we are going to use. This is my eyepiece, through which we will see the spectrum, and these are the apparatus. So the apparatus is optical bench. You know what is optical bench, and the uprights, sodium lamp I have shown to you, and then bi-prism I have shown to you, slit I have shown to you, and this these are the measuring scales for this upright. You can see here there are two scales. One is, this is the main scale, okay, and this is my vernier scale. Okay, this is circular scale. So if I move this, so you can see the motion here. Sure. Okay. So least count, you know already that this is in millimeter. So first you have to find the pitch, and then divide by the number of circular division. So this is already, you know already about the pitch and all these. The formula which we are going to use to find the wavelength of the sodium light is lambda equal to beta 2d by d. So beta is basically the fringe width. What is the fringe width? So we will talk about later. 2d is the distance between the two virtual sources. D is the distance between the slit and the screen, and we have to find this 2d is d1, d2, and d1, d2 are the distance between the two images formed by the convex lens. Okay, So let us first try to understand the ray diagram of this Fresnel Bi-prism. So you can see that this is my source. This is my first source is here, and this is my Bi-prism. You can see this is the base to base is connected. So if you consider that this ray is coming from the source and these two rays, and then they reflected at the base and they goes here like this. Okay, you can see here, and the original direction of this is like they will be going in this direction. Similarly, this will be going in this direction. Okay, but the base they reflected here and goes here. So if I extend this, line, you can say dotted line, this one, it comes here, and then similarly this line, extend this, it come here. So it seems that this monochromatic source of the sodium this distributed because of the distribution of the wavefront. We have two coherent sources, S1 and S2. It seems that because of the two coherent, there are two coherent sources. If you see from this side, you will see there are two coherent sources. The rays are coming from the two coherent sources. Okay, and what happens when the rays we'll see when the rays are coming here, like you consider this is going here and then going here from this other source, it is going here, and similarly these are meeting it here. So this whole region, this one, you can see this to this region and this region. This is the overlapping region, because of which the interference happen and we get a band of dark and bright fringes here at this place, okay, at the screen. So this is all about this, what we are going to see in our experiments. So from the coherent source, we get from monochromatic source, we get two virtual coherent sources, and the interference between all these in this region, we get a band of dark and bright fringes. So we have to find the width of this dark and bright fringes, which we have to use, as I told you that in the experiment, this is the beta is the fringe width. So we have to find out the fringe width of this dark and bright between two fringes. Okay, this D is the distance between the slit and the screen. So this is, if I have source is here, slit is somewhere here near the source. So from this position to the screen, that will be my capital D. And D1, this 2D is basically, or I can see 2D is basically the distance between this S1 and S2. This is 2D. But we cannot, because these are two virtual sources, there are method to find the distance between these two sources. So there is provision to find the D1 and D2. You can see here between S1 and S2. So we will put a convex lens between the screen or eyepiece and the Bi-prism, and then we have to find out the two images at the different positions, and this will give D1 and D2. And then we will use this 2D is D1 by D2 under square, and then is basically we have to use in this formula. Okay, now let's come to the procedure. So the first thing you have to do is to level the optical bend by using the split level, and then the second thing what you have to do is use take this slit part, the upright on the slit, and then I have Fresnel Bi-prism mounted here on this another upright, and I have the eyepiece. The second part is to let them together and ensure that the height of all these are in a line, okay? Because the light source which are coming from here has to fall directly on the slit, and from the slit the light source must fall on the edge of this bi-prism, and then from here to the eyepiece. Okay, so you must level all these things into one line. So the line of this which is coming here has to be parallel to the optical bench line. Okay, if it's not so, then there will be the lateral problem. Okay, so let me fix it near to at 0 position, near to the source. The slit is there. Make the slit sharp and bright, and then take your bi-prism near to the source, and you can see that the upright of this has the two movement. So one movement is that with that let me explain you that I can, using these two, I can shift this like in this direction, and the other one is using this very fine, I can shift this into in this direction. Okay, so I can move this like this and also in these directions. Fine. So let me face it towards the slit. So what I have to do is make the slit very sharp and bright, and from this side you will see from the naked eyes, not using the eyepiece, what you are going to see that is the same thing as I explained you, that where is my slit? Let me find it. Okay, so this is what? So this is my source. The source is coming. This is my source, and source is falling on the bi-prism. Okay, so what if I see from this side? So then I must see two virtual sources, two line sources. So because this is an extended source, if I see from this side, so you must see two virtual source, two lines like this, and in between there will be a very small, very sharp lines in between. So it will be like the two bright lines very close to each other, and in between there will be many small lines like this. Okay, so that has to be very sharp, because the one source, out of the one source, monochromatic source, these two sharp bright lines are the two coherent sources, and in between the interference is there in this, what is this the band you will see in between these two sources. Okay, so you can see it with the naked eyes, and you have to make it sure by the movement, as I told you, that you can do this movement as well as this movement, so that the light falls on the edge of the bi-prism, so that you can see. Only then you can see a kind of situation which I am explaining to you. Otherwise you are not going to see that. So but we have to ensure that you can see, if when the source, this is the axis of the experiment, okay, and axis of the bench. So this will be the axis of the bench, okay, and then this will be the axis of the experiment. Okay, so this line of the light which is going into a straight line. So if these two are parallel, okay, the axis of the experiment and the axis of the optical bench are parallel, and the light is exactly falling on the edge of the bi-prism, then there will be no lateral displacement of the fringe. Okay, and if it's not so, then what will happen? There will be, if the light source is going in this direction along the axis of the optical bench, but I am moving in this direction, so there will be a lateral shift. So what I am telling you that if this happens, that from the naked eye, if I see the two sources, and in between there are lines which are the bands here, and then if they are clear by the movement of this movement, fix along this movement with this fine screw, and along this movement, adjust it very carefully so that you see two sharp lines, and in between you have the fringes, and then you move your eyepiece towards the upright at which your Fresnel bi-prism is mounted. and then try to see from the eyepiece. Okay, so and by the movement of this from this side, okay, or using this screw, you will see a sharp image. If you move it further, and so the fringes, so these fringes, the distance between the fringes, like you will see here. So first you will see that there are two bright lines, in between there are more lines, and then if I move my eyepiece further from the Fresnel Bi-prism, you will see that a situation is like this. You will get more and more, the fringe width are getting more clear, and the well separated together. And then if I move further, then this is getting broadened, and then further this is also getting broader and broader. So now in the eyepiece, if I keep on moving from this side, so if there is no lateral shift, I've told you if there is no lateral shift, then what you'll get a kind of situation from this situation to this situation and to this situation. So when I reach to this situation, what I have to do is I have to find the fringe width now. Okay, what I have to do is I have to fix my crosswire on the bright fringe. So if I start from either this side or this side, don't go this side and then come to this side. So take it to remove the backlash error. Take from either from right to left or left to right. So if I go from this side, so I will choose the first. I will put the crosswire on the first bright, okay, and note the reading. And how to note the reading? That you can see that this, from the help of this, you will see the crosswire and the bright fringes. Here you'll put the crosswire, and then you put the crosswire using this screw and this measuring tape, and then note down the main scale reading and then the circular scale reading, and you get multiplied by the least count. So that will be your main reading. And then very slightly using this micrometer, come to the second brightest. So this is your second bright, and then note down the reading, then this again to the next one and next one. So this is how you take at least 20 readings, 20 bright fringes you choose. Okay. So you see, the first thing you have to find the pitch of the screw. Okay, you see the pitch of the screw. If you rotate from 0 to 0, and what is the movement on the main scale, that is the pitch of the screw, and then the number of division on the micrometer screw, the number of division on the micrometer screw. This you do in screw gauge also, and then you find the least count. Okay, then the moment we get a crosswire on the bright fringe, you note the main scale reading. So it's the first number of fringe, number 1. So I note the main scale reading, 1 year scale reading, and the total. Okay, so I'll go to 1, 2, 3, 4, 5, 6, 7, 8, 19. So because 1, 3, 5, 7, 9, because the first is like bright fringe, the second will be dark. So third will be the again bright. So that's what will be 1, 3, 5, 7, and so on. So I have 1, 3, 5, 7. Similarly, I'll go to 39, 10 readings here and 10 readings here. And similarly, I will note for all these bright fringes, main scale reading, 1 year scale reading, and the total reading. then I'll take the difference of the 20 fringes. Okay, so that means if this is my first fringe and this is my 20th fringe, so I'll take the difference from this to this. Then the third one, and then 20, then there will be 23. So the 23 minus 3, 30, 20. So the difference between the 20 fringes, so 21 minus 1 and 23 minus 3 and 25 minus 5 and so on. I'll find the difference of the 20 fringes, and then we'll get the mean of 20 fringes, and then if divided by 20, we'll get the fringe width. Okay, so this is how we find the fringe width, which we have to use into the formula lambda equal to beta times 2d by d. So this is very simple to calculate from once you get this situation in the eyepiece. Okay, so I'll calculate using these micrometer readings. You'll calculate the fringe width. Now D you can calculate. So D is the distance between the screen, which is my eyepiece, and the source. This is the position of the slit. Okay, so from here to here, this will give me the capital D value. Now we have to find the 2D. To find the 2D, what I have to do is, I have to use a convex lens. So I'll put the convex lens in between the Fresnel Bi-prism and the eyepiece. Okay, and by wiring the, you must know a rough focal length of this convex lens, and you must put this. If the focal length of this is 10, so the distance between between this Fresnel Bi-prism and the eyepiece has to be minimum 4 times the focal length of this. So if it's 10, so I'll put this, and this distance between the eyepiece and this has to be more than 40. Okay, so if we'll get more than 40, and then what I have to do is I have to move this lens between this eyepiece and then the Fresnel Bi-prism. If you do that, at some position nearer to here, nearer to the Fresnel Bi-prism, you will get the 2 line sources. As you see earlier, the 2 sources, in between there were the lines, a spectrum where. So you will see the 2 sources, clear 2 sources, coherent sources, near to the Bi-prism. So and then that position will be the first position, and that is known as the D2 lines. And then if I move further and if I go closer to the eyepiece, the same situation will get the 2 coherent sources, the bigger one, which is the 2 clear virtual sources. So that position is known as the second position, that is the D1 position. So I have to note the D1 and D2. How to find the distance between D1 and D2? So this is what the table is, the first position of the lens. So once I get the first position of the lens, if this is nearer to this, so what I'm going to get is I'm going to get a 2 coherent sources. Okay, so what I have to do is put the crosswire at this and find out the reading, and write the reading of the first image, main scale, vernier scale, and then total, and then put the crosswire at the second image. Okay, and write the main scale, vernier scale, and this. So this will be the D1. The distance between this will be D1. So if I subtract this is going to give me D1. Similarly, if I move towards smartly towards the eyepiece, I'll get again the position of D2, and the same will be there with some bigger lines, and then the difference will be more. So I'll put the crosswire here and the crosswire here, note down the reading of this and this, and take the difference. Similarly, so second position of the lens, first image, second image, and the difference will be D2. So the square root of D1 and D2 are going to give me 2D. So you'll get them if so. This 2D we will use in order to calculate the wavelength, which is lambda equal to beta 2D by D. So beta, how we calculate beta fringe width? D is the distance between the screen, which is the eyepiece, and the source, which is the slit, and 2D is given by in terms of D1 and D2, and D1 and D2 are measured when we put the convex lens in between the telescope, the eyepiece, and the Fresnel bi-prism, and the distance between the Fresnel bi-prism and this eyepiece has to be more than 4 times more than the focal length of this convex lens. So once I have all these things, 2D, D, and beta, you can calculate the wavelength and in angstrom, and that is what we have to find out, the wavelength of this monochromatic source of the sodium. Okay, so the main thing which has to be taken into consideration, that this optical axis and the experimental axis have to be parallel. Otherwise, if there is some lateral shift, then the moment you move away from the Fresnel bi-prism, the fringe you are seeing from the naked eyes, they will shift either this side or this side. So we'll not be able to figure out and the complete fringes as in this case I am seeing here. Okay, thank you.